Welcome to DP Tutorials by Donny Jerwa. In this teaching module, we will accentuate on this brief teaching lesson, which is the temperature dependence of resistance. And in this teaching lesson, we will try to derive the expression of temperature coefficient of resistance. Now, we have learned that conductors always have these free electrons, and inside these conductors, when we pass electric current through such conductors, all these free electrons will be moving on one single direction. Say, if this end of the wire is positive and if this end of the wire is negative, so all these electrons will be moving in one single direction, constituting to the flow of current. So, in addition to the movement of the electrons, it is certain that there will be collision among the electrons. Suppose if this is electron number 1 and this is electron number 2, so there will be collision among these charged particles or electrons. This will cater to what we define as our resistance. So in the previous discussion, we have derived a relation to find out this resistance, the expression for resistance. Okay, so the expression for resistance is given by this formula: R equal ml divided by Ne square into tau, where m is the mass of the electron, L is the length of a given wire, N is the electron density, E is the charge of the electron, E is the area of cross-section of the wire, and tau is our relaxation time. Now we know that as we supply electric current to a wire, if I have a wire like this, that means as electric current passes through the wire, there will be potential drop across these two ends of the wire, and simultaneously there will be what temperature experience on the conductor, like when you touch an electric bulb. If I have an electric bulb and if I touch the surface of the bulb, even though if it is lighted, there will be some heat dissipation on these electrical appliances. So which means that the resistance of the filament of an electrical appliances will have some temperature associated with it. So this temperature in which it is dissipated on all electrical conductors or electrical appliances should be with regards or should be associated with what? With resistance. So from here, when the temperature of the conductor, it is also experimentally found that when the temperature of the conductor increases, then the number of collision of all those electrons also will increase. And due to the increase of these number of collision of the electrons, that means what will happen to the time in which they collide, the time in which those free electrons collide, what will happen? It will decrease. So the resulting in increase of what? Resulting in increase of resistance. So from here, let us put an assumption. The derivation will start from this particular heading. That means, and suppose I will consider this resistance time graph. Okay, let this be the plot along the along the x-axis. Let us plot resistance curve, and along the y-axis we will plot the temperature curve. So that is your resistance, and along this part we will have what? We will have the temperature. Now let suppose at a temperature of 0 degrees centigrade, the resistance of such conductors be R0, okay, which means that even though if the temperature of the conductor is 0 or at room temperature, that means still there will be what? Still there will be resistance. So at T degree centigrade, the resistance of the conductor, not temperature, the resistance, the resistance, okay, let the temperature be, we will put over here 0, okay, let the temperature be 0. And then at let the resistance, okay, we will put over here let the resistance of the conductor be R0, and let at t equal to t, suppose over here at this particular point, suppose at a temperature of t equal to t, let the resistance at this particular point be RT. Suppose at this particular point it is RT. That means we know that as temperature increases, resistance will also increase. So which means that at this particular point, okay, okay, the resistance of the conductor will be how much? The resistance of the conductor will be RT. So I have initialized over there that let RT be the resistance of the conductor at the temperature of T equal to T. And over here this will be the negative side of the temperature. So from here, let the resistance at T equal to T, let the resistance at T equal to T be equal to RT. Then the change in temperature will be the change in temperature. The change in temperature, that means delta T. The change in temperature delta T. We used to put the change as one as delta T. The change in temperature delta T will be equal to 1. Will be equal to T degree centigrade to T minus 0 degree centigrade. So over here this will be T minus 0, which will be equal to 1, which will be equal to T. Then the change in resistance. The change in resistance will be 1 delta R. So this change in resistance will be equal to 1, will be equal to RT minus R0. This change in resistance will be equal to 1 R, okay, RT minus R0. RT minus R0. So that is the change in what? Change in resistance. So this is RT minus R0. RT minus R0. So now it is evident that the change in resistance, this change in resistance, when I talk about the change in resistance, it means that this is the expression. This is the expression for the change in what? Change in resistance. RT minus R0. So over here, this RT minus R0 will be the change in resistance. Okay, it will be the change in resistance. Then this change in resistance will depend upon two factors. It will depend upon two factors. Number one, that means this delta R, which is the change in resistance, it is directly proportional to the initial resistance. What is the initial resistance? This is our initial resistance. This R0 is our initial resistance, which means that is this delta R, that is this delta R will be equal to will be not equal, it is directly proportional, it will be directly proportional to R0. Okay? R0. So this will be the first condition. That will be our first condition. Then next, the second condition is that this change in resistance is directly proportional to the rise in temperature, which means that delta R is directly proportional. Okay, delta R is directly proportional to the change in temperature. What is the change in temperature? The change in temperature will be that T. Okay, this change in temperature will be T. So we will mark this as condition number 2 or equation 2. So from these two equations, this will be the plot for metals and this will be the plot for these semiconductors. So from these two equations, we can write down the following expression, which means that from here it implies that this change in resistance is directly proportional, number one, to R naught, and number two, to the change in temperature, which is T. And from here, in physics, we have to replace this proportionality sign by keeping an equal sign and a constant of proportionality. So from here, that constant of proportionality we will denote by another symbol, which is alpha. Okay, this is alpha, and this alpha is a constant which is known as the temperature coefficient of resistance. So what is this alpha? This alpha is our constant, and it is defined. Okay, it is defined as the temperature, okay, temperature coefficient of resistance, temperature coefficient of resistance. Now we will mark this as a relation number 3, and from there we also know that that change in temperature, okay, that delta R, okay, that delta R, this delta R is nothing but the temperature of the resistor of the conductor at temperature RT minus the change minus the resistance of the conductor and R naught. Delta R is the change in resistance. That means resistance at T equal to degree centigrade, at T equal to T degree centigrade, and at T equal to 0 degree centigrade. So we'll put over here. So this will give you RT minus R naught, and this will be equal to alpha. Okay. Okay. This is your alpha R naught into T. So from here we are interested in finding this alpha. Our target is to find what is this alpha. So alpha from here, okay, that alpha from there, that alpha will be equal to 1. Will be equal to, of course, multiply this R naught T to the denominator of the left hand side. So we'll get RT minus R naught divided by R naught, divided by R naught into T. So this is our final expression for the temperature coefficient of resistance. Okay, temperature coefficient of resistance. This is our expression for the temperature coefficient of resistance. And from here, keep in mind that this is also the plot for the resistance temperature plot, the resistance temperature plot for what? For a semiconductor. For a semiconductor, that means as temperature increases, resistance will decrease. So we will study about this in the later section. When I talk about semiconductors, I'm stressing about what? I'm stressing about examples such as diodes. Okay, we have also these devices such as what? Such as a transistor. Okay, all these are known as what? All these are examples of what? Examples of semiconductor devices. And from here, we should learn also something about what? About the SI unit. So what is the SI unit of this alpha? When you look, okay, when you look from this expression of alpha, okay, so from here on the numerator term, it is resistance and resistance, so it should be ohm, and on the denominator term, R naught is also ohm, and over here it will be what? It will be degree C. So ohm and ohm will get cancelled, so you'll get only degree C inverse. Okay, degree C inverse. So this is the SI unit. Degree C inverse is the SI unit of what? Of temperature. So which means that alpha, the SI unit of the temperature coefficient of resistance is what? Is degree C inverse. Degree C inverse. So this is the units. Okay, this is the unit of temperature coefficient of resistance. Now, based upon the temperature coefficient of resistance, we can classify this into different materials. Okay, we have metals, we have semiconductors and insulators. When we talk about metals, that means we are catering to what? Semiconductors, which means from here that that means before we go into those special cases, that means this temperature coefficient of resistance is the change in resistance. From the numerator term, it is very clear. RT minus R0 is what? RT minus R0 will be the change in resistance, and R0 is what? The initial resistance into what? Change in temperature. So what is the definition of the temperature coefficient of resistance? The temperature coefficient of resistance will be defined as what? As the increase in temperature. This will be when I talk about increase in temperature, that means I'm stressing about this part. This numerator term will be what? The numerator term will speak about the increase in temperature. Increase in temperature per what? Per unit original temperature. This is our per unit original temperature. This is your original temperature. And per degree rise in temperature. This is the degree rise in temperature. So now we will move on into the special cases. So when you look closely into that expression, for alpha, we have, okay, that alpha will be given by what? Alpha will be given by the expression RT. Okay, this alpha will be given by the expression RT minus R0 divided by R0 into T. Suppose when this RT minus R0 is equal to 0, it implies that this RT, this difference of RT minus R0 will be what? It will be positive. So when that is positive itself, it means that this expression also will be what? This expression will be positive. So when, okay, when this the temperature of such conductors, that means the temperature of such conductors at T equal to T is more than the resistance of, when the resistance of the conductor at a higher temperature is more than the resistance of the conductor at a lower temperature, then temperature coefficient is positive. So if temperature coefficient is positive, it means that these types of materials are what? Are metals. So which means over here that when, okay, when this RT minus R0 is 0, then, okay, then this alpha will be positive. Our temperature coefficient of resistance will be positive, and this will be purely for what? For all conductors. All conductors will have what? All conductors will have positive value of temperature coefficient of resistance. Okay, that means conductors, if you have this conductors such as what? Such as aluminium, such as copper, such as silver, okay, such as gold, okay, all these will have positive values. All these will have what? Positive values of temperature coefficient of resistance. Okay, that means as temperature increases, okay, as temperature increases, such for all these types of materials, as temperature increases, okay, as temperature increases, it means that the resistance also will what? The resistance also will increase. Okay, the resistance also will increase. Resistance will increase. Okay, resistance will increase. As temperature increases, resistance will increase. Then another important special case is that what happens when the temperature of such materials at a temperature T equal to T is less than R0, which means that this will be for that case for one, for a semiconductor device of this form. That means when this is the plot of the temperature, and this is your resistance axis, temperature axis. That means from here, as T increases, what will happen? The resistance will decrease. That means when this T increases, when the temperature increases, the resistance of such conductors or such devices will decrease. Which means that over here, when you look from this expression of alpha, that means that numerator term RT minus R0, that means when this is very small than R0, when this condition holds true, it means that the numerator term, this difference will be what? That difference will be negative. So when that is negative, it implies that this expression of alpha also will be 1. Alpha also will be negative. So such type of materials where alpha is negative, it means that this will be the types of material which are known as what? Which are known as semiconductors. Semiconductors, all the values of the temperature coefficient of resistance will be negative. So semiconductors will have negative temperature coefficient. Examples such as what? Such as a PN junction diode, okay, such as a transistor, okay, such as rectifiers. All those will be what? All those will have negative values of temperature coefficient of resistance. So that means over here, which means that as the temperature rises, as the temperature rises, what will happen to the resistance? The resistance will decrease. That is why we recommend to use these types of semiconductor devices for most of electronic sophistication, okay, electronic gadgets or electronic construction. So as temperature increases, the resistance will what? The resistance will decrease. Resistance decreases. So another important illustration, okay, is that what happens when RT equal to R0. So from here, when you look at that numerator term, when RT is equal to R0, that means over here RT equal R0, you can put that RT by R0, so you get R0 minus R0, so this will be equal to 1. That will be equal to 0. So when that expression is equal to 0, which means that over here I can rewrite over here RT minus R0. This is the main expression. This is the main expression for temperature coefficient of resistance. Okay, this is the main expression for the temperature coefficient of resistance. So from here, this will be 0. Okay, that will be 0 based from this derivation, and over here this will be R0 divided by T, which implies that alpha will be equal to 0. Alpha will be equal to 0 if and only if, short form of if and only if is IFF, if and only if RT is equal to R0, which means that this will take place only for materials which are insulators or bad conductors of what? Bad conductors of heat and electricity. So this is that condition. This is that condition, and it will be 0. Okay, this condition will hold true for materials which are known as what? Which are known as insulators. So materials whose temperature coefficient of resistance is 0 are known as what? Are known as insulators. Materials whose temperature coefficient of resistance is negative are known as what? Are known as semiconductors. Materials whose temperature coefficient of resistance is 0 are known as what? Are known as insulators. And materials whose temperature coefficient of resistance is positive, all these materials, okay, all those materials are known as what? All these materials are known as what? Are known as conductors. So these are the three types, okay, three types of on the basis of alpha. Okay, on the basis of alpha, we can categorize, okay, materials into three types, okay, conductors, semiconductors, and insulators. Remember, with regards to resistivity also, we can classify materials into three types. Okay, we can classify materials into three types. We have conductors, okay, same way, conductors, that means semiconductors, and what? And insulators, Over here, the resistivity of insulator is very large compared to the resistivity of what? Of semiconductors. Okay, okay, SC of semiconductors, and the resistivity of semiconductors is even more than the resistivity of what? Of the resistivity of conductors, which means that conductors always have poor values. Okay, conductors always have poor value of electrical resistivity, the least value of electrical resistivity. And inductors, insulators will have what? Will have the highest value of what? Of electrical resistivity. So what is this rho? This rho is nothing but our term which is known as what? As our resistivity. Okay, our resistivity. So remember all those key features. Okay, remember all those key features. I will just draw and highlight again. Alpha for conductors. Okay, alpha for conductors. So alpha for conductors, and this will be for one. This will be for semiconductors, and this will be for one. This will be for insulators. So for conductors, okay, for conductors, alpha is 1. Alpha is positive. For semiconductors, alpha is 1. Alpha is negative. And for insulators, alpha is 1. Alpha is 0. Temperature coefficient of conductors is positive. With the increase in temperature, the resistance also increase, so temperature coefficient also will be positive. With the increase in temperature, the temperature coefficient with the increase in temperature for conductors, resistance decreases, and hence the temperature coefficient will be negative. Over here in insulators, that means the temperature is almost equal for at any point. Okay? At any point, as temperature increases, it will have always the same value of resistance. So just go through all those discussions which we have discussed, so that you will understand, okay, the clear idea and a clear picture of what is the relationship, especially from here. The SI unit, okay, this SI unit is very important. The SI unit of temperature coefficient of resistance is very important. Okay, it is what? It is degree C inverse. Degree C inverse. So just go through your this analysis of this discussion so that you will comprehend. Thank you.